Uh, Hello. In this lecture, we are going to do. We are actually doing the method of images. Okay, and just let me share the screen, and then we'll continue. Okay. So yesterday we were doing a method of images only, and we were doing some cases where intersection of two conducting planes are there. We did a case on dipole placed in front of a infinite grounded conducting plane. We also did a case of a conducting ring placed in front of an infinite conducting plane. Also, we did several other cases likewise. Also, we did a case where an infinite line of charge was placed, whose nearer distance from the infinite conducting plane was given as L, and such problems were being done yesterday. Okay, so and then actually I was doing a problem which had this kind of thing. I think if I have to explain, then uh, this was, I think, done. Okay, so let me reiterate the problem for the people who have joined, did not join yesterday and have joined today. So let me redo the problem. Okay, so yesterday the last problem that I was discussing was about this, that I had these two infinite grounded conducting plane, and I had this lambda. This lambda is what? This represents your linear charge density. So a linear charge density, a line of charge which is parallel to z-axis was placed at a distance, at a distance, uh, at point A comma B. So at a point A comma B, you had a line of charge which is parallel to z-axis, and these are x and y-axis. So basically, it is perpendicular to the plane made by x value. And we wanted to find what is the induced surface charge density and induced linear charge density because of the on these planes, because of the presence of this particular line of charge which is running parallel to z-axis. Okay, the first thing that I wanted to develop was that if I'm supplied with an infinite line of charge, what would be the potential at any distance r? So at any distance r, the potential will be given by minus E dot dr. And while I was calculating it, I told that since in this particular case, this is an infinite line of charge, it implies that my charge would vary from minus infinity to plus infinity. So you can no longer take infinity as the reference potential here. So for that, you have to take some point r naught. So some point r naught is there where you assume that your potential is zero, because at infinite this will blow up. If you want to see this, this goes in log, and if I place infinity as my reference point, this will go to like it will diverge. And that indeed should be the case, because here you do not have a interactionless state at infinity, so you cannot no longer take infinity to be the point where your reference potential is zero. Okay, so we take in general some point r naught where your potential is assumed to be zero. So by that formulation, at any distance r, if you have a line charge density at any distance r, the potential can be given by lambda upon 4 pi epsilon naught ln r naught plus square divided by r square. Now, if this lambda is placed at point A comma B, and I told you that why I'm not discussing this thing in three-dimensional case, because again the problem is this infinite line of charge goes on from minus infinity to plus infinity. Also, that I'm more concerned with finding what is the induced charge density on these two planes. This plane runs parallel to y-axis, and this plane runs parallel to x-axis. So obviously, I will discuss only the case two-dimensionally. So here I want to first find what is the potential as a function of x, y. Okay. Now, so let us take any point x comma y. If this is your lambda, so by method of images, you will have minus lambda here. Because this is lambda, you will have another minus lambda here. And if you draw a boundary here, so if I draw my boundary here, you can see that this boundary should contain no charges. Why it should not contain any charge? Because see, if this is it is an infinite conducting, these two are infinite grounded conducting planes, and if a lambda is placed, if a line of charge with a linear charge density lambda is placed, what will happen? Because of the presence of this charge, an equal and opposite charges will be induced on these surfaces. So in totality on these surfaces, you will have a induced linear charge density which should be equal to minus lambda. So if you draw a boundary around it, in this boundary, the total charge must be non-zero. So total charge must be non-zero. Total charge must be zero. Okay, or it's similarly, if you make a boundary around it, so you have this lambda. Because of this lambda, you will have minus lambda here. Because of this lambda, you'll again have a minus lambda here. Now, in totality, if I do not place a lambda here, my boundary conditions won't be satisfied. So, and also you can see because of this lambda, there would be some potential at origin. So you need some lambda or some charge density here to negate that. So one of the possibilities is that you can place a lambda here. And this is what we have verified also later on, that I developed a potential as a function of xy in general. So forget about these conducting planes. Always remember, whenever I'm doing this method of images, like let's say this is Q, and let's say this is my conducting plane. When I place my image charge here, basically it is equivalent to removing this particular thing. So this is what we have done in method of images. We replace this problem by an auxiliary problem which satisfies the boundary conditions. So what is the boundary condition? The boundary condition suggests that my potential should be zero. Okay, because it is grounded, so your potential should be zero. So in order to maintain that, you need an image charge. Now you have an image charge, potential would be minus kq upon r. Here it will be kq upon r. So in totality, the potential would be zero on this plane. Similarly, when you have this lambda here, so instead of minus lambda, you will have an image minus lambda. One lambda is there, so another image will be minus lambda, and another one would be lambda, which ensures that the total boundary contains no charges. Also, you have to remember one formula, which you have done in your ray optics, that the number of images for intersecting mirrors is 360 degrees divided by theta in degrees minus 1. So this will give you number of images. So for example, if your planes are intersecting at 90 degrees, then there would be 3 images, and this is how it would be. Now, if I tell you what will be the potential as a function of xy, so what it would be? So I have to take the distances from here to here. I will have to take distances from here to here. I will have to take distances from here to here. I'll have to take distances from this point to this point. And in this place at r, I will write the distance. R naught is some reference potential, so I'll get a potential. So potential as a function of xy I got in this fashion. And I also verified that whether my potential on these two conducting planes is it zero or not. So at x equal to, on x-axis your y is zero. So I placed y equal to 0 here. So wherever I placed y equal to 0 and then I calculated it, I found that my potential is 0. And if I place x equal to 0 for this particular plane and I check it, so I'll again get a potential as 0. So if you put in these expressions x equal to 0 and y equal to 0, then you'll find that your potential is 0, which indeed should be the case because these two conducting planes are grounded. So basically, you should not have any potential at these points. And in order to justify this, only we have kept these image charges. Is that clear to you? I think Bharat will be clear about it, but Rajit and Vritti have joined today. So is that clear? Not clear?
Yes, sir.
Okay, good. So in any case, what would be the induced surface charge density? So one of the ways in order to establish this is, see, you find a potential on this. You find potential on any, let's say, whatever plane is there, okay? And once you find this potential, you just find the normal derivative of this potential. So the normal derivative of the potential give you electric field in the normal direction to the plane. So let's say this is your plane, this is your axis, this is your y axis, this is your x axis. So normal to this is x and normal to this is y. So what I'll do in order to obtain the electric field, what I'll do, I'll differentiate with respect to x here, I'll differentiate with respect to y here. So that is what I've done. I found the normal component. And another property of conductors is there that just near the conductor, the normal component is given by sigma upon epsilon. So this will give you an idea of induced surface charge density. So we obtained induced surface charge density. Okay. And once we obtained surface charge density, we were interested in finding what would be the total linear charge density induced on these, you can take surfaces or you can say on these axes. So what is the linear charge density which is induced? Because see, these are infinitely extending. So the extension is infinite. So I'll take what I'll do. See, if I would have integrated sigma dx into dy, then it would have given me what is the total charge. Okay, but this is a single dimension, no? It is a single dimension, right? So that is a difficult thing to do. So what I'll do, I will find what is the linear charge density induced. So for that, I will just integrate sigma with dx. What is sigma? Its dimension is charge per unit area, and here you have some length element. So this length element will cancel one length element, and you will get what? Charge upon length. So basically, when you integrate sigma dx, you will get linear charge density. Okay, so we wanted to find what would be the linear charge density induced at y equal to 0. And for this, we use these two formulas. That is, we found induced charge density on plane 1 and induced charge density on plane 2. And accordingly, we've obtained induced charge density at y equal to 0 as minus 2 lambda tan inverse A by B, and induced charge density, induced linear charge density on x equal to 0, which happens to be the y-axis. It was minus 2 lambda upon pi tan inverse B by A. Now question arises that if I had placed a line of charge with a linear charge density lambda here, in totality, for both of these planes, contribution from both of these planes, what would be the induced linear charge density, what you can think of? So one can instantly say that, okay, if you place a minus lambda here, so total induced charge densities, linear charge density on these two planes would be equals to minus lambda. Is that clear? This is what one expects. Okay, and let us see if that is the case or not. So we have obtained charge densities, linear charge density induced on both of the planes, that is both of the axes, you can say. So at y equal to 0, we've obtained, and at x equal to 0, we've obtained. So in totality, let us add them up. So what is minus 2 lambda upon pi tan inverse B by A and minus 2 lambda upon pi tan inverse B upon A. And you take minus 2 lambda upon pi common out. And remember, tan inverse x plus tan inverse 1 upon x is pi by 2. So pi by 2 will come here. It cancels. You will get total induced linear charge density is minus lambda, and which indeed meets our expectation. So this is the last question that I was doing. Okay. Bharat, is that fine?
यस सर. सर एक डाउट है.
बोलो जी.
सर ये हमने सरफेस चार्ज पे लीनियर चार्ज का निकाला है ना हमने सर. दोनों जो इनफाइनाइट प्लेन्स है उन पे एक्चुअली में सरफेस चार्ज इंड्यूस हुआ ना.
हाँ जी,
सिग्मा
हाँ जी.
ज्यादातर हम लेते हैं क्योंकि
Yes.
प्लेन्स है उसमें. सर फिर हमने ये लीनियर चार्ज मतलब वो समझ नहीं आया था मेरे को.
वो इसलिए बस इसलिए किया क्योंकि द क्वेश्चन वाज गिवन इन दैट फॉर्मेट में. सो देखो, क्वेश्चन इस फॉर्मेट में दे रखा है कि इट वाज गिवन दैट यू हैड अ इनफाइनाइट लाइन ऑफ चार्ज लैम्डा. Okay, so question, we got a question where we had this lambda. So an interest of the author or probably the book should be that what would be the induced surface charge density, induced linear charge density. Had I placed a charge q here, then I would have been interested in finding the charges. Probably one can also find that also, like sigma dx into dy one can do. But again, like I'm not very sure. Look, like what is the information given to us? So that is one thing. So
sir, I mean this linear charge density, it's not necessary that it will induce a linear charge density in the two-dimensional surface.
Yeah.
It is not necessary, no?
Yeah. I've got your point. Look, what you are saying is probably that if it is a plane, and why you are not finding charge here, and instead you are finding lambda, like linear charge density, and which you are
Yes,
not
sir.
very convinced that on the surface how to express this kind of lambda. Although you might have been, you might have got whatever I say mathematically, that if I integrate sigma with respect to a length element, I would obviously get a linear charge density. Yes, this is what I feel that you are saying, right?
Yes,
So
sir.
probably like this is from this is from Jackson. So what he wants to do probably is because he's written this lambda here, so he wants to he wants to put things in same variables only probably. And also I need to confirm this up. But overall, have you got the point?
Yes, sir.
Okay, so mathematically it is quite intact. Okay, but physically, I'm also not very sure that why it has been done that way. Okay, chalo. So let us do another question and then we'll move ahead to a different topic. And today we'll start with Laplace transform on mathematical side. So at least we have something new to do. Okay. Okay. So let us do another problem, which is again intersection of these things, like planes only. And just give me a minute. Okay. Just give me a minute. Okay. I'll bring the problem. Just give me a minute.
सर ये टॉपिक कर रहे हैं तो हम वो इंटरेक्शन एनर्जी बिटवीन डाइपोल्स वो वाला भी इसमें कर सकते हैं वैसे।
Okay. Sorry for the interruption. Let us do this question. Okay. So question says that there are two planes, infinite grounded conducting planes. So I'll write it here. So we have two semi-infinite grounded conducting planes. Let us take this problem at first. And always remember this problem method of images needs a certain sense of symmetry. Okay, it needs a certain sense of symmetry. So this is inclined at 60 degrees. Okay, and charge q is located at the bisector. Okay, a charge q is located at the bisector. I have not made it a complete bisection, but it is located at the bisector. So it is 30 degrees, it is 30 degrees. Okay, at a distance d. So this is your distance d. At a distance d from the point of intersection. So from the point of intersection at a distance d, you've placed a charge q. Okay, and these two are infinite grounded, semi-infinite grounded conducting planes. So here you have potential 0, and here also you have potential 0. And now one wants to find potential. We have to find potential at a point S. At a point S located at a distance small r. So located at a distance small r from the point of intersection. Okay, so we have to find the potential at point S located at a distance smaller from the point of intersection. Not point of intersection, from the from the charge. Okay, so is charge q से at a distance, let's say S, let's say R ना, एक point बना लेते हैं हम लोग कहीं, यहाँ पे हमें पता करना है what is the potential. So let us say this is your point. Let's say this is your point P from the charge, no, not point of intersection. So from the charge Q. Okay, so this is your R. Okay, so, and this is your D, this is your R. Is that clear? Question is clear? I hope question is clear.
Yes, sir.
Okay. So how to start the problem? Okay, how to start this problem? I think this is a little bit difficult. Let me try. Okay, let me try. So what I'll do, because there is a, and also remember, for method of images, you need this certain sense of symmetry, because if it is not located, then it will become slightly complicated problem. At least for exam also, that will become very complicated. I will do that case, like I'm thinking to do that case also, like a general case for theta. But right now, let us do this case. Okay, so let us first make a, इसको थोड़ा ध्यान से ही करते हैं, तो एक बार इसमें गलती हुई फिर अपन पागल हो जाएंगे इसको सही करने में. Just give me little bit time for this. So shapes, this is image. Okay, so one thing is for sure, this is your y-axis, let's say, and this is your, let's say, x-axis. Okay, and your charge is located at 60 degrees. Okay, so what I'll do, so I'll just make let's take this here, and okay, so I'll write 60 here. So this is 60. One has to understand that. And another thing is that your charge is located somewhere in the bisection of it. So your charge is located somewhere in the bisection. So this is fine. So somewhere in the bisection, you have this charge to located. Okay. And this plane is also like sort of infinite rounded conducting plane only. Okay. So what will happen? Because of this infinite rounded conducting plane, there would be image formed here. Is that clear? Okay. Another thing that I want to inquire, how many image charges one can expect? How many image charges one can expect? Is Kriti there? How many image charges can you expect here?
So 5.
5. Okay, so 360 divided by 60 degrees minus 1, you have 5 image charges. So one image charge would be C here. Another image charge, because of this, see this, I should make, what should I do? I want to make it somehow understandable to you. ठीक है, so ये जो मैं red में बता रहा हूँ, it does not exist as of now, but बस सिर्फ बताने के लिए कि यहाँ पे एक plane था. Okay, okay, यहाँ पे ये दो planes थे. Okay, and ये इसके intersection पे कहीं बीच में. ठीक है, now see, because of this charge Q, there would be another like this is 60 degrees ना, कितना है ये degrees में? It is 30 degrees from here. कि ये देखो मैं तुम्हें समझा देता हूँ, ऐसे टप 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 टप, तो ये हो गया 30 डिग्रीज, ये हो गया कितना डिग्रीज? 30 डिग्रीज. इज दैट क्लियर? ये चीज समझ में आ रही है, ऊपर से जा रही है? देखो एक तो इमेज चार्ज यहाँ बनेगा, दिख रहा है, एक इमेज चार्ज यहाँ बनेगा फॉर श्योर, और एक इसकी वजह से एक इमेज चार्ज वहां बनेगा. इज दैट क्लियर?
Yes, sir.
ओके, एंड सी अभी
सर
एक और
पे क्यों ड्रॉ किया आपने?
ओके ओके, दैट इज व्हाट आई एम फिगरिंग आउट. दैट देखो यहाँ पे कितना एंगल है? 30 डिग्रीज, राइट? यहाँ पे एंगल कितना है? 30 डिग्रीज. और यहाँ से यहाँ एंगल कितना बच रहा है? 30 डिग्रीज. मतलब सोचो मेरी बात, दिस इज योर 60 डिग्रीज, इजंट इट? दिस इज योर 60 डिग्रीज, उसके आधे में, लाइक उसके बाइसेक्टर पे यू हैव दिस चार्ज क्यू. सो इफ दिस इज 30, इट विल, दिस चार्ज, इमेज चार्ज वुड बी सिमेट्रिक टू दिस. मतलब जैसे मैं कैसे समझाऊं चीज, जैसे मान लेते हैं ये था हमारा, सो एग्जैक्ट सिमेट्री पे था ना, जैसे ये लेंथ L दूर था, तो इट वाज आल्सो एट अ डिस्टेंस L ओनली ना.
ओके सर, गॉट इट सर.
Angular symmetry wise, if I talk, it will come here only. Is that clear?
Yes sir.
Okay, and magnitude wise, okay, sorry, this is magnitude. This will be minus Q. So don't forget that thing. This will be minus Q. If this is Q, this will be minus Q. If this is Q, this will be minus Q. Is that clear?
Yes sir.
If you'll do any mistake, then things will go at wrong way. Okay, this is minus Q. Because of this minus Q, there would be again some Q here. There would be again Q here. So this image again imaged over like this plane, you will have again Q here. Why this Q will come? See, you have to place somehow 5 image charges. So one of the expected locations was that if I am placing my charge Q here, I will have my charge minus Q here. If I have charge Q here, at an angular symmetry of 30 degrees, because this is 30, so it will go 30 degrees beyond. So minus Q would come here. because this plane is still there, no? So this plane is there. So what will happen because of this minus q, one can write image charge here. That would be now positive because this is image of image. Okay. Is that clear? Now, because of this charge, at exact opposite, you will have another charge here, which is q. And again, the same problem. If you make a boundary over it, this is minus q, this is plus q, this is q minus q, q. Total q plus q plus q, 3q minus q. So you have these two minus q's, right? So minus 2q and q. This is minus q and then these two q's. So total q is there. So you need one negative charge as well. So what is one ideal location to place it? So if this is q, I will place at exact symmetry minus q here. And if you want to, like this is a, if you want to make, you see this is 60 degrees. So what will happen if this is at 30 degrees? So this will also be at 30 degrees only. Okay. And this will be at 60, this will be remaining 60 degrees. So what is happening? This is 1, this is 2, this is 3, this will be, I think, 4th side, this will be, I think, 5th side, and this will be, I think, 6th side. And if you see that all these, see for this minus q, there is an opposite image here. You have this q here. Okay. So if you see these images form vertices of regular hexagon. Is that fine? Okay, this is what we did when we were doing a single charge placed in the intersection of 90 degrees. So we had formed a, if you join all these image charges, you can form a regular square here. So here, instead of a regular square or some regular pentagon, you have this hexagon here. Is that fine? See,
yes, sir.
This will be 60 degree here. This again will be 60 degree here. So I think this is quite clear. Okay, now the calculations are obviously, I think it will be difficult, but at least you've got some idea to it. Is that clear, Kriti? इसको समझ में नहीं है. I don't know. Is she there? I mean, I don't know. अच्छा, we two are only there now. Okay, so just give me a minute. इसको थोड़ा सा ढंग से कर लें, नहीं तो फिर बाद में things will not be अपनों समझ में आना बंद हो जाएंगे. ठीक है, तो हम लोग मानते हैं वापस से वही कि हमने जैसे मान लेते ये हुआ हमारा एक, ये मान लेते दूसरा. अरे यार, this is like second. Now we'll make a pentagon type of thing. So you have this charge q, you have this charge q here, you will have minus q here, you will have, I think, minus q here, then you will have plus q here, then you will have minus q here, and then you'll have q here. So what will happen? This will form a side of a hexagon. Okay. And now you want to find potential at a distance x, at a distance r from this. You want to find potential at a distance r from this charge. Is that clear? And what was the distance from here to here? The distance here to here was, I think, d. Okay, is that clear? I think this is quite clear now. The diagram is quite clear. This is 30 degrees from here, and this is 60 degrees. Okay, so let us mark it. Like for example, ये क्या लिया था हमने? P लिया था, इसको S ले लिया था. Let us take it as P1. Let us take it as P2. Let us take it as P1. इसका image को P2 लिख देते हैं. ठीक है. और अगर ये P है तो इसकी image यहाँ पर बना लिया हम लोगों ने. Let us take it P1 P2 and then I will take P1 P2. P3 तो अपने को मिल जाएगा नहीं, कहीं पे भी लिख दो यार आप. P1 इसको ले लो, इसको P2 ले लो, इसको P3 ले लो, इसको P4 ले लो, इसको P5 ले लो, कोई दिक्कत नहीं. ठीक है, इसको P0 ले लो. चलो P रख लेते हैं, जो दे रखा था वही ले लेते हैं. ठीक है, डन. यहाँ तक कोई दिक्कत? ओके. अब हमको क्या देखना है? हमको डिस्टेंसेस कैलकुलेट करनी पड़ेंगी. सो सबसे पहले ये डिस्टेंस देखते हैं. तो ये डिस्टेंस जो कि वो कितनी होगी, सोचें. व्हाट वुड बी दिस डिस्टेंस? थोड़ा सा मतलब बचपन वाला क्वेश्चन हो गया. व्हाट वुड बी दिस डिस्टेंस? सो दिस एंगल इज, आई थिंक, 60 degrees. है ना, because this is 30, तो remaining will be 60. So just find me P1s. What would be P1s? So by law of cosines, you clearly can understand that your P1s would be root over it will be this distance. This distance कितना होगा, ये distance कितना होगा, ये हो जाएगा ये distance d दे रखा था ना, right? थोड़ा सोच के करना पड़ेगा. So this will be, I think एक बार ढंग से लिख ही लेते हैं ना. So this will be इसको O लिख देते हैं. So P1s would be O P1 का square, and then this will be plus OS, यहाँ से यहाँ तक का distance पूरा लेना पड़ेगा, OS का square, and then there will be minus 2 OP1 OS cos of 60 degrees. Is that clear? Is that clear?
Yes, sir.
Okay, and this distance is d, right? So this distance is d. Sorry, this distance is d. This angle is 60 degrees. अरे यार, क्या गंदगी हो रही है. This angle is 60 degrees. अच्छा, अब देखें ये 30 हो गया. ये 30 मान लेते हैं, ये 90 हो गया, तो ये भी कितना हो जाएगा, 60 आई गेस. बट अपने को थोड़ा सोचना पड़ेगा. एंड ठीक है, ओके. और अगर ये d है, सो आई थिंक जितना मेरे को ट्रिग्नोमेट्री आती, जितने मेरे को ज्योमेट्री आती है, दीज हेक्सागन्स, ये जो एंगल्स होते हैं, ये जो ट्राइंगल्स होते हैं, दे आर इक्विलेटरल ट्राइंगल्स, इफ यू रिमेम्बर. ये तो अपन सोचे
Yes,
कि,
sir.
है ना, तो ये इक्विलेटरल ट्राइंगल है. तो अगर ये डी है तो इसके सेम ये वाली साइड होगी, ये भी होगी डी, राइट? तो मतलब ये जो डिस्टेंस है यहाँ से यहाँ तक, ये कितनी होनी चाहिए, डी. समझ पा रहे हो मेरी बात, मैं क्या कहने की कोशिश कर रहा हूँ?
Yes, sir. Yes, sir.
सो दिस विल बी रूट ओवर डी स्क्वायर प्लस ओ एस का स्क्वायर. तो ओ एस का स्क्वायर कितना हो जाएगा, इट विल बी डी प्लस आर का स्क्वायर. इसको डी प्लस आर अपने लेने के बजाय सीधे वही लेने का पॉइंट ऑफ इंटरसेक्शन से, लाइफ इजी हो जाएगी इतनी. कम से कम क्वेश्चन तो इजी हो जाएगा. नहीं तो डी प्लस एस, फिर ये क्या करेंगे इसका. हम्म, समझ पा रहा हूँ, मतलब ये एक काम करते हैं, थोड़ा सा वेरिएबल चेंज कर देते हैं
Yes, sir.
क्वेश्चन में, तो ये बहुत लंबा हो जाएगा. फिर एक डी और ए डी, इसके बजाय लेट अस टेक दिस डिस्टेंसेस आर, कम से कम लाइफ इजी हो जाएगी. लेट अस टेक दिस डिस्टेंसेस आर. ठीक है, ये डी है कोई बात नहीं. लेट अस टेक दिस डिस्टेंसेस आर. नहीं तो फिर वो दो डी, फिर आंसर तो हालांकि थोड़ा मोड़ा अंतर हो जाएगा, अगर मतलब कोई बात नहीं. सो व्हाट आई वांट इज, लेट अस टेक दिस एज आर. सो दिस विल बी माइनस 2 dr cos 60 कितना होता है, आई थिंक हाफ होता है. So this will be like this. So this will be P1s. So your P1s will be root over d square plus r square minus d, right? Is that fine?
Yes, sir. Yes, sir.
Okay. And if you see this side, like this wala, ये वाला, this P15, what would be P5s? Sorry, P5s. What would be P5s? So P5s will be root over this distance. यहाँ से यहाँ तक ये कितना है, d. ये एंगल कितना है, 60 degrees. And again this distance from here to here, since this is r, यहाँ से यहाँ तक इसको r बोल दिया अपन लोगों ने लेटेस्ट में, बिना मतलब इसको टाइम वेस्ट नहीं करते, यहाँ से यहाँ तक अपन लोगों ने r ले लिया. So if this is r, हाँ जी बिल्कुल,
सेम ही आएगा सर इसका तो.
हाँ एग्जैक्टली सेम, वही मैं कहना चाह रहा हूँ. बिकॉज दिस इज r, दिस इज d, दिस इज 60 डिग्रीज फ्रॉम हियर टू हियर. और अगर ये 90 है ना, सो ये 90 है. और फिर अगर अपन सोचे थोड़ा सा, तो दिस P15, ये P5s का डिस्टेंस, ये कितना डिस्टेंस r है ना. सो P5f would be again is equal to P1s, right? This is what I want to convey. See, because ये पूरा पूरा डिस्टेंस r है, and this is d, और इसके बीच में एंगल कितना, 60. यहाँ पर ये था d था, और ये r था, और इसके बीच में एंगल कितना था, 60 डिग्रीज. इज दैट क्लियर?
यस सर.
है ना, मतलब तुम करके भी देख लो इसको. तो P5s कितना होगा, तो P5s will be root over d square, and then it will be plus r square minus 2 dr cos of 60 degrees. इस तरीके से करोगे तो अगेन यू विल गेट द सेम थिंग. सो आई विल राइट हियर P5s. I will write P1s is equal to root over d square plus r square minus OTR. Is that clear? ये चीज समझ में आ गई. प्लस उस ज्योमेट्री ज्यादा है इसमें, ठीक है, पर जो है जो
Yes,
है,
sir.
ठीक. ठीक है. और r मैंने इसलिए ले लिया, नहीं तो फिर मेरे को d प्लस r का स्क्वायर लिखना पड़ता तो ये और लंबा हो जाता फिर. ठीक है, इसलिए मैंने r पूरा ही ले लिया. ठीक है, यहाँ तक कोई दिक्कत तो नहीं. What would be
No,
your
sir.
है ना, what would be your this P4s? What would be your P4s? So I'll make a line from here to here. बस गंदा हो गया अभी डायग्राम. I cannot help. What would be your P4s? So for P4s, one thing is sure that you need two distances. One is OP4. What would be OP4? OP4 would be again D only. But this angle then would be, and this is R. This is R. But this angle is now no longer 60. This is now 120 degrees. Is that clear? This angle I'm talking. This is OP4 and this is OS. And this is P4s. Is that clear?
Yes, sir.
So your P4s would be equivalent to writing root over d square plus r square minus 2dr cos of 120 degrees, which again would, I think, be equals to root over d square plus r square plus dr. Is that clear?
Yes, sir.
What would be P2s? Here, मतलब ये वाला जो है ना, sorry, ये P2s.
Equal to P4s only.
It will be equivalent to P4s only because see now again angles are, so if I make this, so this is like D here, this is 60, 60, 120. So in totality is 120. So P4s will be equals to P2s and P2s will be equals to P4s and this is it. ये दो distances पकड़ में आ गए. अब रिमेनिंग कौन कौन से डिस्टेंस चाहिए हमको? एक तो हमें चाहिए PS वाली डिस्टेंस जो कि सिंपली हो जाएगी, आई थिंक अगर इसके हिसाब से चले तो R माइनस डी, जो नया लोकेशन है अपन उस हिसाब से चले तो PS वुड बी R माइनस डी. Is that clear? And what would be P3s? P3s would be R plus D. Is that clear or not clear?
Yes, sir.
Okay, so now I'll write the potential at point S and then I'll solve it in the next lecture because this is going to end very soon. But I'll write the potential. So what will your potential at point S? So it will be, this is minus Q. At P you have plus Q. So I'll write K Q upon PS. What is PS? 1 upon R minus D. At P3S you have a negative charge, so I'll write minus R plus D. Okay. Then you have two same distances, P4s and P2s are same. So I'll write at P4 and P2, there are both positive signs. So I'll write plus 2 divided by root over R square plus D square plus RD. And then I'll write minus 2 root over, if I'm not wrong, R square plus D square minus RD. Is that clear to you?
Yes, sir.
And we'll discuss the case where R is way, way too greater than D. Okay, so that we can use binomial expansion. Okay, so that I'll do in the next lecture. Is that fine? यहाँ तक समझ में आ गया?
Yes, sir.
Okay, so I'll meet you in the next lecture.